Chapter 5. Substitution ciphers. This chapter covers simple substitution and polyalphabetic substitution ciphers, solving polyalphabetic ciphers using the Kasiski test and the index of coincidence, auto key and running key ciphers and methods for solving them, simulating rotor-based cipher machines. We are now ready to explore the basic tools described in the preceding chapter in greater depth. Before I begin describing all the various ciphers, let me explicitly state the goals that these ciphers are trying to achieve. The Dutch linguist and polymath August Kirchhoffs first expressed these principles in a pair of articles in Journal des Sciences Militaires in 1883. 1. The cipher should be unbreakable in practice, even if not in theory. 2. This should be true even if the enemy learns the system. 3. The key should be easy to remember, without notes, and easy to change. 4. It should be possible to transmit the enciphered messages by telegraph. 5. The apparatus and documents should be easily carried and operated by one person. 6. The cipher should be easy to use. There should be no complex rules or computations. Rule 4 might be updated to read, transmit the enciphered messages digitally. Otherwise, these precepts remain as valid today as in 1883. One corollary of the second principle is that the strength of the cipher should reside solely in the key. Kirchhoffs also believed that only cryptographers are qualified to judge the security of a cipher. Too often the decision of which cipher to use is made by government officials who lack cryptographic expertise, sometimes with disastrous consequences. Section 5.1. Simple substitution. Simple substitution, also called monoalphabetic substitution, is the familiar type of cipher you see in the puzzle sections of newspapers and magazines. In simple substitution, each letter of the alphabet in the message is replaced by another letter of the alphabet consistently and uniformly. So, if the letter M has been replaced by T in one place, then every M in the message will be replaced by T, and every T in the ciphertext will represent an M. Since most people are familiar with the techniques for solving simple substitution ciphers, I will merely mention them: letter frequency, initial letter frequency, final letter frequency, double letter frequency, letter pair frequency, short words, common prefixes and suffixes, distribution of vowels and consonants, pattern words, and exploiting the punctuation. For the easy cryptograms in newspapers, often all that is needed is to look at the short words. If you find AB and CBA, the words are probably to and not, while AB and BAC are most often of and for. The pattern ABCA is likely that. ABCDC suggests there. ABCDB could be which. If you search the internet, you may be able to find lists of pattern words for sale, or websites that will find words matching a pattern you supply. For the more difficult cryptograms with texts like Foxy, Pixie, Manx, Axed, Toxic, Luxury, Onyx, Sphinx, a more organized approach is needed. I demonstrate the procedure using the following sample cryptogram. The language is known to be English. The text has 73 letters and 11 words for an average word length of 6.64 letters, versus 5 letters for normal English. The absence of short words of fewer than 5 letters and the absence of pattern words suggests that this cryptogram has been deliberately constructed to be difficult. The first phase is to identify vowels and consonants. Begin by counting the number of occurrences of each letter of the alphabet to get the frequency count. In the sample cryptogram, the letter count for A is 0, B is 3, C is 3, and so forth. The full frequency count follows. Notice there are only two high-frequency letters here, L and S, with frequencies of 8 and 7. In normal English text there are 40% vowels. This percentage is robust and usually holds even when the letter frequencies have been deliberately manipulated. With 73 letters in the cryptogram, there should be 29 vowels. That pretty much requires that both L and S represent vowels, unless the frequency has been severely skewed. Next, you make a contact chart by listing the letters of the alphabet vertically down the center of the page. Each different letter that appears in the cryptogram gets its own row. On each row, each letter that appears before the central letter is listed to its left, and each letter that appears after the central letter is listed to its right. For example, the first row of the chart, E, O, B, D, W, Z, means that in the cryptogram the letter B is preceded by E and O once each, followed by D, W, and Z once each. Here is the full contact chart for this cryptogram, shown in 3 columns to save space. The contact chart is used to identify vowels and consonants. In general, vowels contact a wide variety of letters on both the left and the right, while consonants tend to have a limited number of distinct contacts. From the contact chart we can identify 4 probable vowels, L, Q, S and V, and 4 probable consonants, E, O, R and U. Let's mark these letters, degree sign for vowels and X for consonants, and see if the distribution seems plausible.